Okay, so welcome everyone this morning. We're here today to hear from the EBIO project about electrochemical routes for bioliquids transformation. Very niche topic, but very interesting and groundbreaking. So I'm going to pass over now to the project coordinator, Raman, and he's going to introduce the speakers for you today.
Thank you, Emma. Just before starting with the first speaker, I will just show the program. So just one word about EBIO. That's a project that has now run for 1.5 years. And the idea is to upgrade bioliquids using electrochemical routes. And the topics we will discuss today are very much the focus of this project, which are the oxidative depolymerization of lignin, Kolbe oxidation to remove acids, and also the hydrogenation. We will start with a presentation by Sigi Waldvogel. He's professor at the University of Mainz. He's group leader of the electrochemistry group, doing a lot of research in the fields of transforming organic molecules using electrochemical methods. And a large part of this is also to convert bio-based molecules. So Sigi, the floor is yours. I will stop sharing and you can start.
Okay, I try to share my talk. Then we just have to make it bigger and a laser pointer. So, yeah. So I'm all set. Okay, Roman, many thanks for the kind introduction. And we talk about oxidative lignin depolymerization. It was mentioned that we work with bioliquids, and what I'm talking today is, of course, we use electricity for that, and I call this often the dark side of the green world. As you know, especially in Germany, we switch off our nuclear power plants, and for several reasons, but mainly climate reasons, we also stop the coal and gas firing. Like we go to regenerative electricity. The supply doesn't fit to the demand. This is one of the biggest problem. And keep in mind that a country like Germany is still a heavy industry country. And therefore, everybody thinks about the battery, but the battery have to be really huge. More or less, you need the biggest lake in Germany, the Lake of Constance. You should have to lift 400 meters higher and to have enough hydropower for at least 1 day. And this is not possible. Therefore, we have to make more electricity and use the surplus electricity to make valuable chemicals out of it. And this is one option which could be done. And how we tackle that is usually that we start with screening. That's our technique. That means that there's a kind of screening device which gives you a relatively good results, but precise results that you can use it later on for the more advanced development. And make enough electrolysis on one magnetic stirrer. We use different electrodes, different electrolytes. You can have almost infinite number, but you can have to think about the costs and all the environmental impacts. And then we look into the, for example, divided cells coupled by mass spectrometry. And all the other things could be optimized as well. And you can make it your own if you have a good workshop, or of course, there's a company who provides it as well. This is the undivided cells. That's how we start the screening. Then we go to larger cells, and then we know how to make and convert a large significant amount that you can have material later on for testing on rock solid yields. In many cases, you can go directly from the screening scale up to the synthesis up to 200 grams. You see that later on. Therefore, this is more or less, let's call it like this, our backbone. But if you go to larger quantities, then you have to think about a flow cell. And the flow cell is usually the smallest part of the whole system because you have to work up later on. The workup is usually done discontinuously, and therefore we have this typical kilowatt equipment what we use. That means more or less our heart is definitely the screening, and then we have to decide to use a kind of a batch type cell or flow cell. With flow cells, you go up to 5 kilowatts, but then you have a lot of heat you have to manage. Therefore, at that point, we have to think if you go in this direction a little bit further, or we stop somewhere here where we make at least kilogram quantities overnight. Well, we're talking about bioliquids, and one source, the biggest source of bioliquids is, of course, the paper mills. And of course, the paper mills usually are based on the way that you have cellulose, and this is this driving force that you get the fibers out of that. And then you have some stuff which is left over, lignin, hemocellulose, turpentine, and crude tall oil. These are usually in the graft process, which is left over. And many of them are bioliquids. And that's what was mentioned before. There we talk about lignin, but there are also crude, the turpentine fraction. I'm not talking about that today, but there's also the tall oil. That's also bioliquid and an extremely carbon or hydrocarbon rich version. I would just make a brief note to that before we go to the lignin. Well, if we have the crude tall oil, then you can easily fractionate that, and you get the TOFA. That's the tall oil fatty acids. You cannot use these fatty acids for nutrition purposes because there's some chain links in there which are for mammals toxic, and therefore, but you can use it for material things. And one thing is which will be talked later on, definitely from our colleagues from Holland, is the Kolbe electrolysis. It's a marvelous reaction, and you can kick out CO2 equivalents. This is the typical way which is done, but besides the Kolbe, which was more than 170 years ago, Hofer and Mei found a way, if you do it in this way, especially with a substitution pattern here, then you generate more or less a cationic species which is trapped by alcohols or water itself. This is a way to functionalize molecules and may enhance even the traverse of it. In most cases, you can make double bonds if there's no water or no methanol as a base there. But I will briefly show you that we use that and just lower the oxygen content in that we make the double bonds in there. They have usually already double bonds in a long chain, but then we have more double bonds in there. And the important thing is definitely if you have something like this, then you are able to have systems which have multiple, if the double bonds are epoxidized, then you have multiple epoxy groups there, which are of course interest for making resins. And that's what we indeed did here. We used oleic acid, but also TOFA. And this is the oleic acid, linoleic acid, and this is TOFA. And the amount of by electrolysis, you enhanced the iodine number. The iodine number just tells you how much iodine would be consumed if you remove the double bonds. The bigger the orange part is, the better it is because you have more double bond equivalents in there. And if you have it there, the other double bonds don't make problems in this reaction. And you can do the electrolysis is scalable. We started at 5 milliliters and we went up to 1.4 liters. And then you see, okay, with this amount, you can do something, you can play around. And I think this is the important thing. How does a typical cell look like? What we have here is called stacked cell. That means you have to contact all of the electrodes. These are graphite electrodes. And you just have to check it on the outside to keep the temperature constant. And we work about 200 grams of TOFA in there. You see, we need DC 7.5 angstrom at 5 volts. And this works relatively nicely. And the good stuff is the solvent can be directly recycled and reused. And there's no need for chromatography because the electrolysis is almost clean and smoothly made. Then you use that to make the epoxidation, which is some standard protocols were used here. And the important thing is here, you have extremely low viscosity, which is unusual. And if you compare that, if you make a thermoset of that with cyclic anhydrides, these are common ones which are used. We just don't use these fossil-based versions, which we use here, something which is biogenic derived, and the thermoset you get here is remarkable. The qualities are quite nice. Depending on the anhydride, you get different qualities in when the thermoset starts. The low viscosity is of interest because then you make something you can make very fine structures out of it. And therefore, I think that there's a way to use the tall oil in this way. Okay, let's come to the lignin. And what is lignin about? Usually it's one of the most, let's call it the second most abundant biopolymer. The first is cellulose, and it's almost everywhere. And especially in the pulping mills, it's a side stream, which is in most cases not really utilized. These are the building blocks which can be in there. It depends a little bit which kind of species you have. If you have spruce, then you have mostly this one here. If you have beeches or grasses or something like this, then the syringol derivative is a little bit more prominent. The amount from pulping industries of lignin is extremely high. We're talking about annually 130 million tons. In most cases, it's not isolated. It's just directly concentrated with in the black liquor, and the black liquor is incinerated to get back the chemicals, the inorganic chemicals. Therefore, it's mostly used for energy production, but not as a material. And the question is, can we get out some interesting compounds? And the one compound which is, of course, appealing for many people, and it's also, of course, something which was already pioneered almost 100 years ago, and then brought also in production, for example, from lignosulfonates by Beauregard, that you make vanillin out of it. This is this molecule which is the most important fragrance at the moment. But also aroma chemical. There's a standard reaction which is used quite often is nitrobenzene oxidation, and nitrobenzene oxidation has the highest yield you can usually obtain, but you cannot use this for production because you reduce the nitrobenzene and you make a lot of a variety of carcinogenic and toxic compounds, and therefore it's just as a standard reaction which tells you how much vanillin can be taken out of the relatively diversely connected lignin polymer. Doing this by electrochemistry, we use a kind of an undivided cell, and you see it as 3 molar caustic soda. And by this way, it should be a little bit more, let's call it mild conditions, simple experimental setup, undivided cell. And it turned out, well, it's possible. We identified quite early already some conditions that we use nickel electrodes, which form nickel oxide hydroxide. Then you get nickel, this lignin particle, which disintegrates and forms vanillin out of it. You see already that these were the initial conditions. It turned out if you have different metal-based anodes, which form this oxide hydroxide systems, the cobalt systems outperform all the other ones. But unfortunately, cobalt is not stable in these conditions, and you have some corrosion. You see no corrosion with the nickel systems, and therefore you stay more or less with the nickel system, which is maybe not the best at the very beginning, but it's the way how to work. How can we get a little bit more out of it? And for the planar anodes, they're corrosion stable, but unfortunately, the decent yield in vanillin is not too high. Therefore, we have to improve that. The problem with this planar, that means you have a certain surface area which you cannot enhance in that way, and the current density have to be relatively low. A good solution is to go to nickel foams because you get them very easily for different applications. It's also corrosion stable and it's porous. You can go for geometric current density, which is much higher, and this gives an improved space-time yield. Therefore, the optimization for the lignin degradation seems to be given. Then we just have to go to the other parameters, and it turns out that the higher temperature seems to be better. What is the reason for that? The lignin particle is a little bit like a gummy piece, and at higher temperature it becomes a little bit more floppy, and then the product is a little bit more liberated. The question is, can you go in the electrolysis over 100 degrees? And the way to do this is, of course, that we go in the autoclave, and with an autoclave we are able to exceed the boiling point of water, and it has to looks a little bit more massive, but it has to withstand more or less 10 bars. If we do so, then we enhance already the yield for the vanillin there. And if we correlate that with the nitrobenzene oxidation, we already reached 60% of the relative vanillin yield of the nitrobenzene oxidation. That means There's still some way to improve that, but already 3% is much better. We have usually all the sister compound is the acetovanillone. This comes along with all of these degradations. The question is, does it make sense at higher temperature to have a foam electrode or to have a planar or nanostructured one? We did this with a laser. And it turned out at 160 degrees, it makes absolutely no influence anymore because the kinetics are so fast by the temperature that you don't have problems or that you have to generate a specific electrode system. Therefore, at that high temperatures, you can work with simple planar systems. And then we play around with different lignin versions, and it turned out if you have specific lignins and you work with that, then you can go over 4%. And you see, we are all the time in the same range of the nickel of the nitrobenzene oxidation. That seems to be quite stable. Then we had a look at different craft lignins which are out there, which you can buy. UPM or Westvaco Westbrook versions of the sigma Aldehyde. And you see that the range is quite clear. The UPM was not so good, but the other ones, which are much cheaper, brought better results here as well. Often we have the problem that we want to make an electrochemical conversion, excuse me, which is not possible because the intermediates are not compatible with the anode. That means whatever we make, you have problems here. And then we cannot do the electrolysis directly in situ. That means we need a kind of Excel approach. Excel means we do not electrolyze everything in one system. We just make a reagent first and add it to it. And this is, of course, of interest because lignin can be degraded in an unselective way and make side reactions, and therefore this could be of interest. And there's one oxidizer I want to show you. This is peroxide carbonate. And it's something you can do, and you can work with that in a, let's call it in a way that you have a kind of buffer with a reservoir that you can even buffer fluctuating currents as well, and you can separate off the hydrogen very easily. If you use that and you have to use the so-called PODIC, the peroxide dicarbonate, then you do at lower temperature the oxidation and at higher temperature depolymerization, and this pays off. If you look at that, you get directly 5% and a significant amount of the acetovanillone, which was before a little bit lower. If you compare this to the nitrobenzene oxidation, we are once more much higher. We are close to over 90% of the reference oxidation. And that means here at that point we are really in a good way. And the important thing is the nitrobenzene oxidation is also a kind of makeup. This PODIC is a makeup chemical for the system. You take out the vanillin and the rest goes back to the plant. The optimization was then done by the design of experiment, and then you can go even higher with the amount. You need less of the corresponding PODIC. Here you see the yield, and if you look a little bit more in detail to that, then you see this is the highest yield, and you can go to the lowest amount of PODIC which is in there to get still 5.5 weight %. And by this way, you are able to make it in a very efficient way. The important thing is that you just have to make PODIC, and this only works at bond-up diamond. But in the optimized version, you see we are still have 6 weight % with 1.8 weight % of acetovanillone. If you compare this, then you're in a different range than before. And this is, at the moment, I think from craft lignin, one of the best ones from commercially available craft lignins. If you look at the food material, then you see if you work that on larger scale, you have vanillin, you have acetovanillone, and a little bit of vanillic acid, but the selectivity is quite outstanding compared to other methods. There's another Excel version I want to introduce to you. That's the periodate, and the periodate can be done also electrochemically in a similar way. Here we need a divided cell, It's a kind of a platform chemical, and you will see you can use the periodate to make different reactions by catalysis and even for API synthesis, but we are looking for our own lignin. And you can convert here, lignosulfonate was used here. We just used that directly electrochemically produced alkaline periodate. And it turns out that you get here a relatively large amount of these iodovanillin out of it, which is a very advanced building block. And you get more than 15 weight% out of the starting material. And you see the selectivity is quite outstanding. Therefore, we have made from wood, more or less more direct building block, which can be used for making API synthesis and more advanced compounds. This is used for making tubulin inhibitors, anthrax inhibitors. You see here you have the cross coupling with metals. Here you have the reductive coupling. Therefore, this building block can be also used to make curcumin derivatives for Alzheimer's disease diagnosis and natural products. And there are more than 20 important applications for this kind of building block. The last part is definitely devoted. We make a conversion, we have a significant low conversion. That means, okay, we can go up to 15%, but the problem is there's still some building blocks we have to separate off. And the question is, how can we get the important compounds out of the system without destroying them? Because these compounds are prone to oxidation. And the way is that we have a kind of absorption, and then we directly go further with that. And the point how this works is very simple. We use an ion exchange resin. That means you have the vanillin. This is deprotonated under these conditions. Then you have vanillate, and this sticks to the resin here, and it cannot be rinsed off by caustic soda because there's a strong interaction. I will come to that in a second. And then you have to neutralize this one here. Then this pops off, and you regenerate the resin once more. And this is a very important point. The lignin particles keep off of the gel type resin, and you can easily can do that, and you just put the small or low molecular weight system in that, and the other ones which is not used could be electrolyzed further or brought back, and the black liquor directly into the mill once more, and the inorganic chemicals are not disturbed. Why does it work even at high alkaline conditions? Well, you have a backbone interaction, and when the molarity of the black liquor becomes higher in caustic soda, then the interactions become stronger, and therefore it works on a really broad range of alkaline media. We can use the simplest one out of there. This is the one which comes in with water filters, and it's a really simplest one which is available, and you get easily 90% of the vanillin out of the alkaline solution by simple rinsing it over of the system. You can even use black liquor, and you get directly from the black liquor. It's not much in there, but you can get all of these guys out of it. And by simple pumping the diluted version over it, you get 74% of the aromatic phenols out of it. Here you see these are the ones you can kick off the system. You have the internal standard. This is the guaiacol, vanillin, then acetovanillin. And there's something which you barely see in the black liquor, but this fits perfectly to the resin. And that's the reason why this enhances on that. This is a still being derivative, which can be used also as an advanced intermediate. Therefore, for a milliliter, you get 1.6 milligrams of these phenols. Then you can rinse it off. You can take the black liquor, which is depleted at small molecular weight phenols, and electrolyze that, and then once more take it out. And therefore, you can combine these methods to enhance the amount of phenols. I have shown you a lot of things today, but bioliquids are very appealing, interesting things, and in combination with electrochemistry, you can do a lot of things out of it. There's one way to get these small molecular weight systems out of it, but the problem is you have to separate them off. And if you make something, you cannot only extract it, or you need something which is compatible with a paper mill. And one possibility is that you just catch it out of the system with this resin, or you can pump it out in a kind of bypass, and then you fix the desired molecules, and then you get already a relatively well-concentrated product mixture out of it. We have new concepts we're using PODIC, peroxyl dicarbonate, and the temperature program is the key here. That means the oxidation at mild conditions is important. Then you have the polymer, which is oxidized, functionalized, and the liberation of the vanillin at higher temperature is something which happens afterwards. And this allows you that you don't over-oxidize the final product. And it's the good stuff is you can take out the chemicals and do not disturb the industrial concept of the pulping system. I'm very thankful to the co-workers because I have the way that I did nothing out of it. Maybe have some crazy ideas, but here you see this was done over the time. We have a lot of collaborators, especially in previous ones, and these are the consortia we are active in. And this is my small group at the beginning of the year. I thank you for your kind attention, and if you have questions, please hit me.
Yeah, thank you, Sigi. Do we have any questions, Emma?
We've just got one question here, so I'll just read it out to you. So Sigi, you showed an autoclave electrochemical reactor, as I understood, without separator, membrane/diaphragm. Isn't the risk that then you convert the product at the other electrode to a significant extent? I'll just reread that last part.
Yeah, I know what maybe.
Okay, all right.
Okay. Yeah, it's an undivided cell. That means there's no separator in there, and it's closed. Of course, we on the cathode we generate hydrogen. This is in the case there, but we do not generate oxygen. As far as we know, and therefore we have no problems about safety issues. And the vanillin is not reduced. We checked that. There's a reason for that, because the vanillin is deprotonated, and then it's an anionic species, and therefore it will be not reduced at the cathode.
Great. Thanks for that. I hope that's answered your question there. And
generally, how much would you lose in performance if you would put in a membrane? If you would go for divided? So is there some kind of estimate?
Yeah. The problem is we cannot go in that high temperature because all membranes which really work nicely, like Nafion, there's a limit about 100 degrees. And every time if you use the snow from a chlorine electrolysis, usually Nafion takes about half a volt of the applied voltage. It has to, if there's a clear benefit out of it, then we use that. If not, we try to keep it simple.
Okay.
Right.
I had one more question. That was, I think, on page 18 or somewhere you showed the different electrodes. It was cobalt, nickel, and
yep.
And there was also, I think, titanium listed.
Yep.
Which had a quite high number. Is that something?
Yeah, this is.
Yeah, definitely.
This is a kind of a specific steel version. You can work with that, but we had problems under these conditions, also in stability. The problem is the aluminum in there. Titanium would be fine, but aluminum in there leads to corrosion. You see that also in the content. If you make ICPRS, then you see that aluminum appears there. And that's not something you want to have because this alloy is quite expensive.
Okay, perfect. So I think we thank Sigi, and if there are more questions popping up, then just write it in the chat and we will answer them during today or during that session. Then let's go to the next speaker, which is Bastian Mei. He's assistant professor at the University of Twente in the group of photocatalysis, and he is dedicating his research on electrode and electrochemical process development. And today he will talk about Kolbe and non-Kolbe reactions to convert organic acids.
Okay, thank you, Roman, for the kind introduction. I try to share my screen now here. And start the presentation. Hope that's working. Not yet. Sorry for that.
Just take your time.
Okay, now I need to find myself back for the E here and go to share. So now it should be possible that you see my slides, correct?
Yes.
Okay, and I have to find, I used just the cursor. Okay, again, thank you for the kind introduction. So I will present today our work that we're doing within the EBIO project on Kolbe oxidation, specifically of acetic acid. And I try to impose to you what are the challenges and also what are the opportunities for using biomass, or specifically pyrolysis liquid, for upgrading and using electrochemical techniques to basically get a better stability of the bio oil that we're using. So even though it was already used or indicated in the previous presentation from Sigi quite clearly that we do have a problem, I'd still like to use this slide because I think it nicely indicates that we're not just having a small issue, but we have certainly a quite large issue. So what you see here on this slide is basically the temperature increase over the last couple of years or last hundreds of years. And in the early or in the late 19th, it was still debated whether or not we have an increase in temperature. But now in the last couple of years, you clearly see that the increase in temperature is even surpassing the error margin that we have in all these kind of measurements. So there is certainly a need to decrease the temperature increase on Earth. And to do that, of course, what we need to do is we need to go from the current fossil-based society to a more sustainable energy resources-based society using solar, wind, and of course biomass. Otherwise, we wouldn't be here in this kind of nice meeting. So specifically, we like to consider biomass because it's an easy to handle liquid and it has a high energy density compared to the other solar-based sources where it's rather easy to maintain and handle, and we do not have any problems with intermittent nature of the source, because whenever we have it, we can also make use of it, which is similar to the current fossil-based society that we have. Of course, in the long run, we will need the solar-based technologies where wind and PV panels are having a large fraction of energy supply, but there, of course, we still need to develop the storage technologies that we do not have nowadays. So the bioliquid that we're talking about is pyrolysis oil, and it has a certain composition, which is shown here on the right-hand side of the slide. And you can see that there are aldehydes and also carboxylic acids involved that make the oil quite unstable, and it actually needs to be upgraded to make it really useful for the current process industry. So in the end, what we like to achieve is by stabilizing the oil is a broader applicability of the oil to really ensure that we can use a kind of cycle as it's depicted here on the left-hand side of the slide, where CO2 is basically being used to grow biomass, and we can use the bio waste to make our bioliquid out of it, stabilizing the bioliquid by removing carboxylic acids and making use of the aldehydes, for example. So there are, of course, current upgrading technologies already available, but most of them are very energy intensive. And of course, we do have a surplus, hopefully, in renewable electricity at some point, which we can already utilize, while we're not having the storage technologies available on scale that we would need to really fully utilize the solar energy that is provided in the near future. So what I'm going to talk about today is specifically is the anodic reaction that is shown here schematically on the right in the cell, where you convert carboxylic acids by so-called Kolbe processes into Kolbe products. And it was already addressed shortly by Sigi, that we have two different routes to use or to utilize carboxylic acids and make Kolbe products, and I will go back to this in a minute. But what I'd like to point out here is that EBIO is not only focusing on Kolbe oxidation of carboxylic acids, but it's also focusing on utilizing the aldehydes and the ketones that are in these pyrolysis oils and making them more useful by, for example, reduction to alcohols. In this way, we would operate our cell in a kind of paired electrolysis and utilize the electrons that we are providing here in a twofold manner, which of course makes any process more sustainable and efficient. So the large advantage of electrochemical processes is that we can make use of the surplus electricity and convert our species that are either harmful or not really useful for the oil that we want to utilize in the end in other processes. So this is the more dedicated scheme on Kolbe oxidation of carboxylic acids, and I specifically already used here acetic acid because that's also the compound that I'm going to focus on throughout this presentation in most detail. So what you have is basically a deprotonated acetate that can interact with the electrode surface and being oxidized by forming this kind of radical. In this stage, we're then losing the CO2. So basically, we're kicking out the CO2, as also mentioned by Sigi, and we produce radicals, methyl radicals, that can be either recombined to form ethane, which is the so-called Kolbe product. Maybe. Now I also found the laser pointer, nice. To form ethane, which is the Kolbe product. Or we can form the so-called non-Kolbe or Höfer-Moss product, where the radical is losing another or is further oxidized and interacting with OH to form methanol. As already indicated in this kind of schematic, of course, we would imply or consider that we have a rather high electrolyte pH to have this mechanism being working. And that's also what has been shown by Sigi, that methanol formation or the so-called Höfer-Moss product formation is more favorable at higher pHs and at intermediate current densities. But I have to point out that all of this has been so far being reported or analyzed in batch reactors, and the product detection was rather based on the end of lifetime of the electrolysis. So there was not a continuous product selectivity detection reported so far in literature. And that's where we started off with our research, because we were really interested in if there are any selectivity changes throughout electrolysis of acetic acid to either form ethane or the Höfer-Moss product methanol. So what is also shown here is that we need a potential at the anode, which is way above the oxygen evolution potential. So to really make use of the Kolbe process, the oxygen evolution needs to be inhibited. And that's what is shown here on the slide. Usually what you observe in the presence of any of the carboxylic acids is that you have first an oxygen evolution regime, which is then kind of terminated, and you have a plateau region after which you have really Kolbe oxidation occurring. So, and of course the intensity or the current density of this kind of plateau region depends on the concentration of the acid that you're using here. But still, even though Kolbe oxidation is known since a couple of years, a couple of hundred years already, the electrode materials, current densities, and also the concentration or the pH of the electrolyte are still discussed in literature. So I just like to point out that, for example, Schäfer in the earlier works pointed out that weakly acidic conditions favor Kolbe oxidation, while others are reporting that Kolbe oxidation is basically independent of pH. But the problem in all of these works is that the real product detection was not done in a way that is nowadays possible using online technologies like online GCs, for example. And that's what we're going to show in a moment. So what is happening in this kind of plateau region? It was advertised that at the anode material, the negatively charged acetate ions are kind of absorbing at a certain potential, and thereby inhibiting the oxygen evolution to occur and favor the the oxidation of the acetate molecule, thereby even favoring then the formation of Kolbe products or non-Kolbe products. And of course, you can imagine that if you have a high current density, so you have a high abundance of these radical species at the surface, that they tend to recombine to form the Kolbe product, while at rather low current densities, you might envision that you're actually obtaining a favorable Höfer-Moss product in the end. So let's see. Before I going to really show our experimental results, I also like to address quickly what kind of electrochemical cell we have been using. And it was a quite poor man's electrochemical cell, meaning a batch reactor, where we used the platinum platinum foil working electrode, and we also used the platinized titanium mesh as a counter electrode. The reference electrode, of course, enabled us to really understand what is the potential of the working electrode that we are using. And we started off with different electrolytes containing mixtures of acetic acid and acetate, and we adjusted the pH of the electrolyte to the pHs as indicated here on the slide. So what we studied then is the applied current density and measured online the gas phase components that are produced, and we of course also did a liquid phase offline analysis to really understand what are the products that are obtained in Kolbe processes. So just to remind you, Faraday's efficiency has been obtained by knowing the applied current density, and we have the volume fraction of our gas, and we have the purge rate of our gas, and of course we need the Faraday constant and the number of electrons that are involved in the process. So before going into the online product analysis, I like to briefly point out how the current potential behavior in the different electrolytes actually is. So if you use a blank electrolyte, which is a pH 2 electrolyte of just an acid, where the conductivity is rather high, you can see that at a certain potential at around 1.8 volt, you're kicking in the oxygen evolution reaction. And with the acetic acid in place, basically pure acetic acid electrolyte, we are having quite low conductivity of the electrolyte, so we are limited very much in current densities that we can achieve. Of course, with increasing pH, that is going to be slightly better, and we already maintain higher current densities, but still you couldn't observe any of the plateau regions that I've indicated previously on the slides occurring in the potential range that has been investigated here. So for us, that's the clear indication that there is no Kolbe oxidation yet occurring. And I will also confirm this in a moment. But before that, I like to point out that at higher pHs of pH 5, pH 9, and pH 12, we could definitely see this kind of plateau region that is indicating the transition between the oxygen evolution reaction from occurring and the Kolbe processes. So the region of interest we are operating our experiments in is then, of course, in the potential range around above 2.8 volts. A peculiar thing here in this pH 12 electrolyte is, of course, this kind of double transition region, but this is just a change in water oxidation mechanism, and the actual plateau transition region to Kolbe oxidation only occurs here at around 3 volt. So we were already quite sure that in low acidic or in high acidic conditions, we do not have any Kolbe products forming, but we will detect Kolbe or non-Kolbe products in higher pH conditions. And that's also what our time-dependent product gas phase analysis told us, that especially at low pHs, you basically form only selectively oxygen. And to give you a hint of what are the conditions that we're using here, we use the current density of 25 milliamps per square centimeter, so which is rather low still, but we were just also limited by the conductivity of the electrolyte here. So if we then go to the intermediate regime of pH 4 and 5, we already could see that there are gas phase products following the Kolbe processes are formed, especially at pH 5. We got 100% Faraday efficiency to ethane. And also point out that there's quite some CO2 evolution here, which is in agreement with the Kolbe scheme that I've shown you before. But what was surprising here is that at pH 4, we already have quite some ethane formation, which is stabilizing after a certain period of time. And we have concomitant oxygen and ethane evolution occurring at pH 4. If we then go to the higher pHs of pH 9 and pH 12, we observed again a quite high Faradaic efficiency for ethane initially, but we also realized that there's a current drop in ethane selectivity, but we couldn't evolve or we couldn't detect any oxygen, which is an indication that, of course, after a certain period of time, the reaction mechanism might change from Kolbe processes to non-Kolbe processes. And what is also clearly shown here in these kind of time traces is that the CO2 evolution at higher pHs is even smaller compared to the intermediate pH regime of 9. And what this means, I will tell you in a moment. But before that, we went for liquid phase analysis, and because we have been using a quite high volume cell of 100 milliliter per minute, the liquid phase analysis by GC didn't tell us anything about any liquid products being formed. But what we got a hint that there is actually methanol formation, but just doing cyclic voltammetry of the electrolyzed solution after a certain period of time, and you could see that there's certain oxidation peaks that are resembling the oxidation of methanol quite clearly. And you could see that at low pHs, this oxidation peak is not present. So to fully confirm that there's actually methanol being formed in the process, we did some dedicated small scale or small volume experiments where we could see that indeed for pH 9 and pH 12, the overall Faradaic efficiency calculated for the process was closer to 80% for ethane, and we formed quite significant fractions of methanol already in the end. And that's exactly where we think is this kind of turnover behavior from the Faradaic efficiency or high Faradaic efficiency to ethane after a certain period of time, and then liquid products are formed. So in the end, this is very well in agreement with what has been stated also by Sigi, that at a high pH, you do have favorable non-Kolbe product formation or whole formation formation. But what hasn't been shown so far is that there is also initially a quite selective processes for the Kolbe process. And we believe if you would operate this in a kind of divided continuous flow reactor cell, we actually would be able to, even at high pH, maintain a high Faradaic efficiency to the Kolbe process. But we were quite intrigued, of course, what is happening and why are we changing the selectivity from Kolbe to non-Kolbe processes. And we've looked at two things. So first of all, we were interested in what is the ratio of protonated versus deprotonated acids. And we could clearly see that around the pH where we could find the highest selectivity of Faradaic efficiency for ethane, we of course have a rather high amount of a deprotonated acid being present at the electrode surface, which is in a very well agreement with the current picture that you have acetate ions being adsorbed at the surface. And of course, at pH 9 and 12, basically we have fully deprotonated acids, which would indicate that we would have Kolbe processes occurring. But what we also saw is that we couldn't find any CO2 anymore after operating at pH 12. So we checked, of course, the equilibrium between CO2 and carbonate and bicarbonate, and especially at the pHs we operated at pH 9 and 12, we could see that there's large fractions of carbonate and bicarbonate being formed in the electrolyte. So we were puzzled by what is the influence of the formed bicarbonate and carbonate ions on the process conditions. And to study this in more detail, we started off with a pre-saturated solution, so where we purged intentionally CO2 before starting operation of the process. And what you could see at pH 12, we already obtained larger, low Faradaic efficiency to ethane, even at the beginning of the entire operation of the electrolysis. So to go more into the detail, we also added intentionally bicarbonate to the electrolyte, and this is a study performed at pH 9, where we added up to 0.5 mole of bicarbonate, sodium bicarbonate, to the electrolyte. And what is quite nicely shown here by the Faraday efficiency to ethane is that we can basically suppress immediately from the start the formation of the Kolbe product, while forming more or less selectively, shown here on the right, methanol as the Höfer-Moss product. So to summarize this all, what we think is happening is that we disturb our acetate film layer by the presence of the carbonate species in the electrolyte, thereby having a possibility to also have interaction of water with the anode layer, and thereby facilitating the formation of methanol in the end. So with this, I'd like to also conclude this talk on Kolbe oxidation. And I think the key take-home message here is that we are having possibilities to selectively tune Kolbe processes to either the Kolbe product or the non-Kolbe product. And this would, of course, be of great relevance if you want to operate this in continuous flow and make use of the bioliquid in the end, and basically design a process where we can decide if we want to form a gas phase product to stabilize our oil, or if we want to even go for an alcohol, which might even increase the energy density of the pyrolysis liquid. So I'd like to thank EBIO and all the partners that are involved here. And I'd like to thank you for your attention.
Thank you, Bastian. Do we have any questions?
Yes, we have one question, and it says, Bastian, very nice presentation. Have you also measured H2O2 hydrogen peroxide at the higher anode potentials?
No, we haven't measured any hydrogen peroxide yet, but we of course are aware that there is also a current trend in hydrogen peroxide formation anodically, and there is also of course the carbonate bicarbonate couple being involved. So if I just go back to this slide, of course we do not account yet for the full 100% Faraday efficiency, and it might be possible that there's some hydrogen peroxide being formed here as well. That needs to be still checked. So, but in the short answer, we haven't checked yet.
Great, thanks.
Sigi has a question or comment.
Yeah, a really nice presentation, Bastian. I really liked it. The only point which we have to consider is the old work, which usually Schäfer has summarized. The concentration of the carboxylic acid is much higher. Usually it's 80 to 90% at least in the mixture. That's something which makes it a little bit different in the reaction pathway. And I'm sure there are many things which are not, everybody takes for granted what Hermann Kolbe said 170 up to 150 years ago. But the point is, there are a lot of things which are not yet really elucidated. If you use specific supporting electrolytes, then you don't get decarboxylation, you get anhydrides and all the other stuff. I think the world is much more diverse than we ever thought.
Yeah, I fully agree. So, which I haven't shown here, of course, if we use supporting electrolytes, Kolbe oxidation is inhibited depending on the type of addition you actually use. But the important part here, I think, is that I think it all still goes hand in hand with what you have also shown in your presentation, when methanol formation is basically being facilitated, right? Because you also talked about additional supporting electrolytes that are used in these cases. And I think what we're adding here is just a supporting electrolyte that influences the double layer structure in a way that it's actually facilitating methanol production. Yeah.
Great, thanks.
I have one more question, Bastian. You basically showed that by tuning the electrolyte, you can really select which kind of products you want. Is there anything one can do with the electrode itself to tune the selectivity?
Yeah, that would be nice. So I can tell you, we tested quite some electrodes already to do Kolbe oxidation, and none of them were yet being active actually. So so far it has been platinum, and we, of course, you know that we're also working with BDD, but then we have a stability issue quite fast. So we are more considering now to use support structures to functionalize these supports with platinum, so that we do not need to make use of thick platinum layers, basically, or like thin films as we have been using here. So to basically just reduce the platinum loading in these cases. But because of the oxidative potentials, of course, the interaction between the support and platinum needs to be very good. Otherwise, you might have just an under etching or so, and then you use your platinum in the end. And yeah, that's something that still needs to be figured out and is on the to-do list.
So it's platinum, which is the choice of.
So far, it's platinum, yes.
Okay.
So I know that there is also some discussion about DSA type of materials, but for us, they haven't worked yet. So.
Sigi, you have another comment, or is?
Yeah, there are many people using DSA, especially in Aachen, Pyrolysis group. And this was already discovered in the late 70s by Russians in Novosibirsk.
Yeah, that's what I said, right? So there's also DSA, but for us, DSA didn't work yet. So but of course, there's also a specific ratio always between the titanium and the iridium, and depending on the supplier, that might actually change. So it's also an electrode specificity then involved that.
Yeah, and the Aachen guys, Pyrolysis group, they make it themselves, and that's the problem. And I think it's a kind of an art to make this kind of electrodes.
Indeed.
And to be honest, it's not something sustainable, because these electrodes are extremely iridium and ruthenium. Iridium is 5 times more expensive than platinum, by the way.
Yeah, because it's just a fraction of the platinum mining, right? So it makes completely sense. No, I fully agree. So it is not the way to go forward. So I think what would be more versatile is to go to materials like nickel, for example. But then, of course, you have to tune the structure to facilitate the layer formation. And we all know that nickel as oxyhydroxide is already quite good oxygen evolution catalyst. So maybe we haven't operated it yet at sufficiently high current densities to make it work. So that's also, of course, an option that we have to evaluate here.
Okay. Thanks a lot, Bastian.
Thank you.
Then we come to our final speaker from the same group. Actually, the group leader at the University of Twente. He's a full professor and. As I said, group leader of the photocatalysis group, Guido Müll. His research focus is also electrochemical engineering, photocatalysis towards all kinds of applications, including waste water treatment, conversion of bio-based molecules, and so on. And he will now talk about the other electrode processes occurring on the cathode side. Please, Guido, the floor is yours.
Thank you very much, Roman. Can you see my screen?
Yes.
Okay, perfect. Yeah, so I will be discussing a little bit more on the hydrogenation of aldehydes. Bastian showed a very nice slide with the distribution of components in pyrolysis oil. And in fact, besides the acids, also aldehydes are components that destabilize the pyrolysis oil and need to be converted, preferably to alcohols. And electrochemical hydrogenation could then be a very nice way to pair up with a Kolbe oxidation reaction in a sort of combined electrochemical process, which you see over here. So if we would have the oxygenated liquids, so the pyrolysis oils, coming in and first do the Kolbe to remove the CO2 and the ethane if in case of acetic acid. And then we could flow the same liquid around a cathodic reaction and convert then the aldehydes by reaction with protons and electrons to make the corresponding alcohols. Of course, then you will have a membrane in the middle, and you will have to transport protons from the anode to the cathode. But this would really be in principle be an ideal process to convert both oxidatively acids and reductively aldehydes to make alcohols. So the first thing that we set out to do and try is take a model system, right? And we were interested in looking at simple aldehydes, C4 aldehydes, and here you see the butyraldehyde, and asked ourselves the following question: how selective can we actually drive the hydrogenation of an aldehyde over copper surfaces? There was some literature that showed us that copper could be an interesting surface to look at. With respect to the evolution of hydrogen, of course, in the hydrogenation reaction, you would like the aldehyde to be converted to the alcohol and do not generate any hydrogen, which suppresses the Faraday efficiency of the aldehyde to make the alcohol. We used a buffer solution of potassium acetate, 0.5 molar. We used a Nafion 117 membrane, a classical H-cell setup that Sigi has shown to you already. And we had in the counter compartment, we had a platinum gauze to produce oxygen in the electrolysis. So what is the result of the first reaction that we looked at? So the butanol hydrogenation that you can see over here, and it depends very strongly on the concentration in the buffered solution that we added. So here you see from 0.0, so nothing, to 0.5 molar of butanol. And what you can clearly see is that the higher the concentration of the butanol is, and the better the efficiency is towards the butanol. And at the same time, we suppress the formation of hydrogen if we go to higher concentrations. So the conclusion here is that it does work, and in the highest concentration, up to 90% alcohol is formed and only 10% hydrogen. But indeed, you need a significant concentration of the aldehyde to reach these high Faraday efficiencies towards the formation of the alcohol. Now, to complicate things a little further, of course you could look at double bonds as well. Before actually showing this, of course, if you have the concentration dependent situation, butanol to make butanol. You could ask yourself, okay, in the course of the experiment, if it's a batch experiment, do you see actually the Faraday efficiency of hydrogen over time increase? And indeed, that's what we see. So here you see the hydrogen Faraday efficiency coming up, and that has to do with the conversion of the butanol in the solution. So we basically, as a function of time, lower the concentration, and therefore we lower the Faraday efficiency of butanol hydrogenation as well. If we add some fresh butanol to the batch reactor, you can immediately see that we suppress the hydrogen and Faraday efficiency again to below about 20%, and we increase the butanol Faraday efficiency again to levels up to about 90%. So similar to Bastian, but for a completely different reason. And having a batch reactor with changing concentrations over time, a flow reactor could really be a good solution to maintain the feed concentration at the same level, and therefore have a constant Faraday efficiency towards hydrogen, which is low, and a high Faraday efficiency towards the alcohol. As I said, we would like to also investigate, say that you would have a double bond in the alcohol substrate that you want to convert. Is the selectivity actually dependent on the absence or presence of double bonds? So are we still able to convert the aldehyde into the alcohol, or alternatively hydrogenate the double bond and then produce an aldehyde, the butyraldehyde that we started off with in the previous example? And of course, we still have in both steps the competing formation of hydrogen. So here there is the selectivity issue here is even more complex than starting from butyraldehyde to make butanol. Now what you see here is the result of looking at this crotonaldehyde conversion. And what you typically see is that here you see 72% is actually going towards the crotyl alcohol. So we're selectively hydrogenating the aldehyde group to the alcohol. So this is the preferred reaction. We do make a little bit of butanol, like 20%, and that's this reaction here. So we have some double bond hydrogenation going on, and we can again significantly suppress the formation of hydrogen. That's the yellow part here, which is about 12%. And again, this is at the highest concentration that we tested. And again, I will not show you the data, but if we lower the concentration of the crotonaldehyde, also the hydrogen selectivity or Faraday efficiency will increase again. And then, of course, the question is, in reality, we don't have a single aldehyde in the pyrolysis oil that you need to convert, but we have a mixture of different aldehydes. And here now, of course, the specificity, I should say, of the molecules towards hydrogenation becomes an important question. And so if we have a mixture of butyraldehyde and crotonaldehyde, which of the two is favored and occurs the most efficient? And what the result shows you is clear here. So this is just to remind you the crotonaldehyde by itself. Here you see the result at half a molar of butyraldehyde that I also showed you already. And here is the result of the combination of half a molar crotonaldehyde and half a molar of butyraldehyde. And then what you see is that the product distribution is very similar to what we actually obtained with crotonaldehyde alone. So this shows you that the surface specificity for the double bonded aldehyde is very high for the copper surface, right? So in the reaction scheme, you see here is the crotonaldehyde. This is very selectively converted again to the crotonaldehyde alcohol, but we do not, or to a very minor extent, convert the butyraldehyde to the butanol. So the question is, of course, why? Could we have predicted this beforehand, that the selectivity difference would be so large for the reactant selectivity in this particular case, this being very reactive and this hardly occurring in the presence of this reactant. So therefore, we resorted to Raman spectroscopy. I'll not go into a lot of detail in the interpretation of all the Raman bands that you see in this particular spectrum. I just like to point out a couple of bands that you see forming as a function of potential. It is also important to realize that if you are dipping your electrode into the reactant solution, that initially the surface of the copper is passivated by a film of copper oxide. And you can actually spectroscopically resolve that by this sort of broad feature that you see in this region of the spectrum. And of course, if you go negative in potential, you see these features disappear, right? They're almost gone here. And that means you have reduced the copper oxide towards metallic copper. So that's one thing that we clearly see happening. And interestingly, when we start from butyraldehyde, we see a couple of bands appearing at sort of intermediate potentials, which we can assign to the absorption of the butyraldehyde in the form of an oxidized butyrate structure that you see depicted over here. So it's a kind of acidic C double bond O that is actually bound to the surface, and the chemical, the double bond is sort of divided over the two oxygens, and in that way it nicely bounds to the surface. And then if we remove the oxygen from the surface of the copper, we simultaneously reduce this sort of butyrate structure, and then we start to see the product, which is in this case butyl alcohol. And then you see indeed these features disappear when we reach the potentials at which we perform the reaction of the butyraldehyde to form the butanol. So in summary, we see at some potentials, we see strongly adsorbed intermediates, let's say, of the reactant on the surface, which becomes partly oxidized by the fact that we do have an oxidized copper surface. But in the process conditions, there's very little adsorbed species, as you can see from the limited intensity of the Raman bands in the spectrum during the reaction. Now, this is completely different if we look at the double bonded version of the molecule. And again, I won't go into detail of all the Raman bands and what they exactly mean. But here we have, again, a very strong intensity peak at about this region of 1300 to 1400, which we can assign again to a similar structure, a carboxylate structure, but now of the double bonded version of the crotonaldehyde on the oxidized copper surface. And again, if we go to more negative potentials, we remove this peak. You see this disappear in the spectra here. And what is left is sort of an intermediate stage here with some new features. But I think the most important thing to point out to you is that now we can clearly see peaks here, Raman bands at about 1680, 1700 wave numbers, which is indicative of both the C double bond O of the aldehyde and the C double bond C of the aldehyde. And the fact that these intensities are so large is evidence that you do get a significant absorption of the crotonaldehyde on the surface in comparison to the butyraldehyde, which, remember, in the previous slide I showed there were hardly any spectral intensities visible. So there is a very strong preference for the copper surface at negative potentials to have this double bond adsorbed on the surface, and that explains the surface specificity for this reactant, the crotonaldehyde, in comparison to the butyraldehyde. Interestingly is that we still don't fully understand that the double bond, even though it interacts strongly with the surface, it doesn't really is activated to hydrogenation. We remember that the selectivity to the alcohol still containing, so the crotyl alcohol still containing the C double bond C in the molecule remains rather high, about above 70% if we start from half a molar. And also the product, these peaks that you see also at negative potentials are now indicative of some adsorbed product, the alcohol, also in higher quantities than that we observed for the butyraldehyde to the butyl alcohol. Okay, yes, and that's shown here, what I explained already. Okay, so that basically brings me to the conclusions and maybe a little bit of an outlook of this work. So copper electrodes are very interesting if you want to do these hydrogenation reactions of aldehydes to alcohols. If the concentration of the reactant is high enough, half a molar gives Faraday efficiencies above 90% in comparison to hydrogen evolution. And here you see the characteristic voltage and current density. The selectivity is strongly dependent on the concentration. I said that already, so that leads to the application of flow reactors rather than batch reactors to maintain a relatively high feed concentration. On oxidized copper surfaces, carboxylates are formed, and once the copper surface is fully reduced by the electrochemical potential, also the carboxylate disappears, and conversion of the aldehyde and perhaps some of this carboxylate to the alcohol is feasible. For the crotonaldehyde, it's different. It's still very selective to the alcohol. The double bond hardly gets converted to as much as only 20%. On oxidized surfaces, we see the same thing, carboxylates formed, and these are then also converted to the alcohol. And that goes really nicely. And finally, if you have a mixture of the two, it's very selective. Sorry, this should be crotonaldehyde. And not so much to the butyraldehyde in conversion. And that leads basically to the thank you slide. This is work continued in the EBIO consortium, looking at also other aldehydes and other electrode materials. And I'd really like to thank BTG. Robbie is here in this meeting for providing us with the conceptual ideas and explaining the relevance of these hydrogenation reactions for the upgrading of pyrolysis oil. Thank you very much.
Thank you a lot, Guido. I have one question. If you think of using or converting those aldehydes at lower concentrations, what other options would you have to reduce the selectivity towards hydrogen?
Yeah, what we've done so far is basically using a copper plate that we roughened, electrochemically roughened to some extent. But I think it's really interesting to look at what if we take smaller entities of copper, and if that there is a sort of surface selectivity that we can tune by modifying the copper surface. From electrochemical reduction of CO2, it's known that the selectivity is very strongly depending also on the morphology of these copper particles. And perhaps that's a way to go. So to play with the structure of the copper to suppress the hydrogen evolution reaction, also at lower concentrations of the aldehyde. But we haven't.
Yeah.
I was going to say we haven't looked at that yet. So this is one direction to go.
Sigi?
Yeah, Guido, very nice talk. Usually I would expect that there will be another reaction going on, that you make a kind of a glycol formation, that you have a pinnacle coupling type reaction, which aldehydes usually like to do. That means that you get a kind of C8 fragment out of it.
Yeah, we have analyzed the liquid with gas chromatography, and we didn't get significant, say, high boilers in our analyses.
Okay.
So yeah, also the selectivities, they're not fully close, but let's say to 95%, we could close the Faradaic efficiency. So it doesn't seem to be a major process that is happening. But thanks for mentioning it, Sigi. We should be aware of this.
If you switch the electrode to classic carbon, you should see that, because this is usually the one which is used for pinnacle coupling.
Okay. Okay.
Welcome. Or what you also can use is zinc. The colleagues from ICT Fraunhofer use zinc. Yeah.
Okay, this is indeed very relevant, because if you want to make nanoparticles or use them in electrochemistry, then typically you use a carbon support to put the particles on. So if the carbon itself is already active in more of these formation of longer chain hydrocarbons, then we should be aware of this. Yeah.
Based on your work with the double ring components, if you then would go to some molecules that contained, let's say, an aromatic ring, would you also expect that they would more selectively bind on the copper?
Yeah, that's indeed something we should also investigate in the next phase of the project. And there is indeed some evidence also from studies of Mark Koper's group in Leiden that aromatic rings indeed like to adsorb quite strongly on electrode surfaces as well. I think they did some work on platinum, but indeed that's a very good question, Roman. We should look at that. And again, I think Raman spectroscopy would be a very nice methodology to investigate if there is indeed, just by looking at the peak intensities, in this case of the ring vibrations, if there is a significant amount on the surface or if there isn't.
Yes, Robbie, you had a comment, a question?
Yeah, no, thank you very much, you all three. It's all very inspiring, I have to say, and especially I like this idea about the specific specific reactions taking place on the surface. And coming back to the question of Sigi, if you take different compounds like different electrodes, like the carbon or the zinc, what kind of changes do you expect then on the specificity of the reactions?
Yeah, it's a difficult word, Robbie. Also had difficulties pronouncing it right. Specificity, yeah. Yeah, that of course this should change. Yeah? I mean the binding strength of a molecule on a metal surface is very much depending on the nature of the metal. So certainly we could also look at other metals to drive these hydrogenation reactions and see if we can. Yeah, I don't know if it's necessarily a bad thing for practical application. If the residence time of your aldehyde components is long enough, first you will of course hydrogenate these, but then at some point the concentration of this, or rather the reactant of this reactant becomes much lower than of the other reactant, and then I think this will kick in. I mean, it occurs at the same potential. But if you like to convert them quicker and that this reaction is not hindered by that reaction, and then you should maybe also change the metal.
Yeah, and we have to realize that pyrolysis oil contains a bit more than 2 aldehyde structures. So
yes.
So
yeah.
there's a long way in front of us.
Yes, certainly. We should increase the complexity. I think that's your point, Robbie. The complexity of the feed.
No, not to increase it, to understand the complexity first.
Yeah. But indeed, Roman is quite right. And what do aromatic aldehydes say? So benzaldehyde, for example, what does that do in the reaction? And how does the presence of benzaldehyde affect, for example, the butyraldehyde conversion? Yeah, that's very interesting to look at.
Sigi, you had another point?
Yeah, I just have a comment. The metal or the electrode plays a crucial role, but don't forget that the supporting electrolyte and the electrode function as a couple. That means you can even tune by taking different concentration, different counter ions. You can tune the specificity of the electrode.
Yeah.
And I think that there are many handles there, and I think there's a good way to believe that Guido will just squeeze it in one or the other way.
We'll do our best, Sigi. Thank you.
Yeah, I'm absolutely convinced.
Emma, were there any online questions?
For Guido, for your section, there wasn't, but
okay.
Thank you. No, it was really great though, really clear and very interesting. That's my comment.
Okay.
Okay, then thanks a lot to all the 3 speakers. It was very, very interesting. If anyone has comments or requests regarding those reactions, regarding the analysis methods we use, the cells we use, whatever, please get in contact with us. And otherwise, please share the videos and have a look at our website. And thanks everyone for watching. Bye-bye.
Thank you.
Thank you.
Bye-bye.
Bye.